This section is about inverses. Recall that a relation is a set of ordered pairs. The inverse relation is the set of ordered pairs obtained by exchanging the coordinates of each ordered pair. The domain of the relation becomes the range of its inverse, and the range of the relation becomes the domain of the inverse. So in simpler terms, inverse relation is when you have a relation and you switch the x and the y values. And that means the relation becomes an inverse. So, for example, in the key concept, notice that set A and set B are inverse relations. So set A contains the point 1, 5. Well, its inverse would be found by switching the 1 and 5 around and becoming 5, 1. So 1, 5 and 5, 1 are inverses of each other. You've got 2, 6. Its inverse would be found by switching the 2 and the 6 around, so that would be 6, 2. And then you also have 3, 7. And what is the inverse of 3, 7? Well, when you switch 3, 7 around, trade the x and the y, you get 7, 3. So inverses and their functions have some special characteristics. On this one, it says that we're going to use the vertices of triangle ABC can be represented by the relation 1, -2, 2, 5, and 4, -1. Find the inverse of this relation. Describe the graph of the inverse. So 1, -2 has an inverse of, when we switch the x and y around, it becomes -2, 1. 2, 5, its inverse would be 5, 2. Notice I'm just switching the x and the y. And 4, -1, what would its inverse be? Well, its inverse would be -1, 4. So what I'm going to do is I'm going to graph these on a coordinate plane and then create the triangles that those 3 points will make. So 1, -2 is right here. 2, 5 is right here, and 4, -1, that's over 4 and down 1, is right here. And then I'm going to connect the points with the triangle. And there you go for the blue points, making that blue triangle. And now I'm going to graph the red points. So -2, 1, so that's left 2, up 1. 5, 2, so that is right 5 and up 2. And -1, 4. So that is left 1, but up 4. And then I will connect those points to make a triangle. And there's that triangle. So notice some characteristics of the two is that the triangles are the exact same size. They are turned a little bit differently, but they are the exact same size. And how are they translated, or how are they moved? Some people would say it's moved with a rotation, and it kind of looks like it's being a rotation, but it's not exactly a rotation because you couldn't twist one of the triangles to match perfectly on the other triangle. What we really have is a flip or a reflection. Most of the time we're used to seeing flips or reflections over the x or the y axis, but there's actually another special line that reflections often occur over, and it's a diagonal line. It's this diagonal line that goes from corner to corner right through the center. So from the lower left to the upper right, just like that. So that diagonal line has a special name, and the special name of that diagonal line is y equals x. So why do we call it the line y equals x? For a couple of reasons. Number one is that every point on that line contains the same x and y values. So if I look at a point that's up here that I just highlighted, that is the point 8, 8. So it has the exact same x and y value. Or at the origin has a point described by 0, 0. Or even way down here, that is the point -9, -9. So notice that the x and the y values are exactly the same. So that's one way of describing it. Another way of describing it is that this is in the form of y equals mx plus b with a slope of 1, because there is no number in front of the x. We assume there's a 1 there. And I don't see anything being added to the x afterwards, and that's because that's the b value, and the b value is 0. So that means this has a y-intercept of 0 and a slope of 1. So Y-intercept of 0, again, is right there at the origin. And then I go up 1 over 1. I could lay another point there. Up 1 from that point and over 1. I could lay a point there and so on. So that's why that point is referred to as the point as the y equals x. So in inverse, its relation and its inverse will be reflections over the line y equals x. So it reflects over y equals x. That's what you're going to see with every relation and its inverse. Most of what we do is to find the inverses of functions, those things that are in function notation. So as with relations, the ordered pairs of inverse functions are also related. We can write the inverse of the function as f of x as f negative 1 of x. So when you write an inverse, there's a new notation that we're going to use, and it's right here. F negative 1 of x. That means that it is the inverse of f of x. That means it's going to have all those characteristics I just showed you with the triangles. It reflects over the line y equals x. The x's and y's get switched around on all the points. It does not mean f to the negative 1 power. It looks like an exponent, but it's not an exponent. It means it is the inverse of the function that is named f of x. So we can also find the inverse of a function by just exchanging the domain and range. In other words, exchanging the x and y values. So we do have a step-by-step process that we can do here on example 2. We're going to find the graph and its inverse. Find and graph its inverse. Where directions are to find and graph, find the inverse of each function, then graph the function and its inverse. So the function we're given is f of x equals 2x plus or minus 5. So it says step 1, rewrite the function as an equation relating x and y. What that simply means is it's going to be a whole lot easier to solve when we replace the f of x with a y. So we know f of x just means it's a function, but it really means y. So I'm going to rewrite that as y equals 2x minus 5. Step 2 is exchange the x and the y in the equation. So remember that an inverse is literally switching the x and the y. So I'm going to put an x in place of the y. I'm going to put a y in place of the x's. So that means it will be x equals 2y minus 5. So notice I didn't switch any numbers. I didn't switch any signs. I just switched the x and the y because that's what an inverse is. Then we are going to solve the equation for y. So I'm going to take that equation that I just wrote, which is x equals 2y minus 5, and I'm going to solve it for y. And I would solve it for y by adding 5 to both sides. So that would give me x plus 5 equals 2y, and then divide by 2. So the 2's cancel on this side, so that gives me y equals x divided by 2. There is a 1 in front of that x, so that means it's 1x divided by 2, which can be written as 1/2 x. And then 5 divided by 2 is 5/2. And then step 4 is to replace y with f negative 1 of x, because we do want to write this as an inverse, in inverse notation, and show that it is the inverse of the original function f of x. So that means I would write f negative 1 of x equals, and it was 1/2 x plus 5/2. So all those steps is the first part of the question, which is to find the inverse of the function. And now we're going to graph the function and its inverse. And notice I've already graphed the green line, y equals x, on the graph itself. This is just to show you how everything is going to be reflected over that line y equals x. So the blue function is the original function. It's y equals 2x minus 5. So that means I would go down to 5 because my y-intercept is 5. And then I would go up 2 and over 1 because my rise is 2 and my run is 1, and then up 2 and over 1, and so on and so forth as many times as I want to. Just keep going up 2 over 1, and then draw a straight line through them. So there's that line. And now we're going to do the same thing with the inverse, which I've made in red. So my y-intercept, it says, is 5/2. Well, 5/2 is 2.5. So I'll go up 2.5 units. And then my slope is 1/2, so I will go up 1, which means I'll still be inside of between two marks on the square, and then over 2, which will place that about right here. Then from that point, I'll go up 1 over 2, up 1 over 2, as many times as I want to do that, and then I will draw a straight line through all of those. And there's that line. So notice how the blue function, which is the original function, and the red function, and the line y equals x all converge at the exact same point. They all converge right here because it is a reflection, and when a point or a function and its reflection touch, they should all touch at the mirror, and the mirror in this case is the line y equals x.